If you're looking at invisible light, the kind of light that the sun primarily gives off, they would be blocking that light to absorb that energy for their needs. So you would see an ordinary star just begin to disappear as they built structures around it to absorb that energy. There's an interesting fact here. Well, there's no such thing as a free lunch in the universe. You can't just take the sun's energy and then have the energy disappear. It manifests in other ways. You know how it manifests? As heat.
So why would the brightest works of intelligence end up glowing in the dark? If you intercept a star's output and run it through engines, computers, and habitats, you don't make energy vanish. You change its form. Conservation of energy and the second law of thermodynamics are not suggestions. They're the operating system of the universe. A star's light is hot and short wavelength. Any structure that harvests it must dispose of that energy at a lower temperature, which means longer wavelengths. Capture enough light, and you'll dim the star in visible bands while creating a new source in the infrared. Think of a shell re-radiating near room temperature. By Wien's law, its peak is around 10 microns, squarely in the mid-infrared. That's the telltale, a cold glow broadcasting the workload of minds. But our galaxy is full of natural infrared emitters, dust clouds, star-forming regions, dying stars, each with their own thermal signatures. Where, exactly, should we look, and what would distinguish such a civilization from ordinary cosmic dust? We look where the energy budget stops adding up. Infrared sky surveys, IRAS, WISE, Spitzer, Herschel, have mapped the heavens in wavelengths where warm objects shine. Natural dust glows across a range of temperatures and often carries spectral fingerprints, silicate features near 10 and 18 microns, or polycyclic aromatic hydrocarbons at 612 microns. By contrast, an engineered radiator designed for efficiency would resemble a nearly featureless blackbody at a narrow temperature, and if it encloses or dominates a star, we'd see mismatched energy, less optical light than expected, more smooth infrared than dust alone would produce. Teams have hunted for this mismatch around stars and entire galaxies. So far, we have candidates explained by dust, and no unambiguous examples of civilizations redirecting most of a star's power. That silence is instructive, but ambiguous. Does this silence imply they're exceedingly rare, or that our mental model of advanced life is simply wrong? It could be both, but physics gives us reason to revise the model. Here on Earth, our power use is tiny compared with sunlight, yet the waste heat is measurable, about a few hundredths of a watt per square meter. Scale human energy 100-fold without changing how we dump heat, and direct thermal emission alone nudges global temperatures several degrees. Any civilization bound to a planetary surface hits that wall long before it becomes star-spanning. Meanwhile, information processing has a thermodynamic cost. Landauer's principle tells us that erasing one bit of information dissipates at least kTln2 of energy. Lower the temperature T, and the energy cost per computation falls. So a civilization that values computation more than conspicuous consumption would migrate to colder environments, spreading out into space where waste heat can be radiated at tens of kelvins, peaking not at 10 microns but closer to 100 microns in the far infrared and submillimeter. They would trade brightness for efficiency, centralization for distribution, spectacle for subtlety. If the smartest path is cold and quiet, is there any reliable trace we can still seek? Yes, even the most efficient life must obey entropy, and that makes the universe an honest bookkeeper. We can extend our search to colder wavelengths, hunting for smooth, featureless blackbody emission, divorced from starlight and inconsistent with known dust physics, thermally uniform structures that lack the chemical fingerprints of natural grains. We can do energy accounting across entire galaxies, not just stars. If large fractions of starlight are missing from the optical, yet reappear as unusually smooth far-infrared emission, that hints at engineering. We can watch stars for engineered occultations, transit patterns too precise, too aperiodic, or too geometrically crisp for rings, comets, or dust clouds. We can probe planetary atmospheres for industrial molecules with no plausible geology, long-lived synthetic compounds, or persistent NO2 in combinations that scream manufacturing rather than volcanism. The concluding insight is simple and directional. Stop expecting intelligence to announce itself with power. Expect it to reveal itself through accounting. Follow the heat, even when it's faint, follow the patterns that nature doesn't favor. And for our own trajectory, measure progress not by how much energy we can swallow, but by how little heat we must spill to do more thinking. In a universe that never offers a free lunch, wisdom is the art of paying the entropy bill with exact change. Like if this was interesting, and hit the subscribe for more.